rather unfamiliar to you. So I have to explain the definition. And then I'll tell you why this is an interesting thing to study. So let's start with the definition. So just a notation. So when we have a vector space, then I denote by PV is projectivization. So this is just a set of lines. And by the way, today in my talk, everything is holomorphic. All manifolds are complex manifolds. So everything holomorphic. I guess this makes sense. Lots of this makes sense in real C infinite category, but just for convenience, everything holomorphic. Okay, so, and then I use the following notation. When you are given a point in the projective space, alpha hat is the cone. So this is the line corresponding to alpha. Okay, and then this assignment to alpha hat, this defines a line bundle, which I denote by this on PV. And this is in algebraic geometry, this is the line bundle O minus 1. But if you are not familiar with this, this is a tautological line bundle. That's the notation. Now let me define what I call a cone structure. This must be used before. A cone structure on a complex manifold. M is a submanifold. C inside the projected by tangent bundle of M, such that now we have the projection to M, and I denote by pi the restriction of the projection to C, such that pi is a proper submersion. So in other words, for each point Cx, the fiber at that point, now this is just inside the tangent space. So this is now a compact submanifold. And usually I'll assume that this is connected because by localizing we can take one component to make it connected. So whenever you have such submanifold, this is called cone structure. That's it. Let's see. And I will usually denote by dimension of Cx. I will denote it by P. The P means the dimension of this fiber. Now, okay, this. Whenever you have cone structure, there's a natural differential system on this C. So there's a canonical Partian system. On the submanifold, this cone structure, and that's defined as follows. So this Partian system is given by a sub-bundle of the tangent bundle of C in the following way. So for each point, the fiber at that point is just this guy, where d pi alpha is the projection from the tangent space of the the cone structure to the tangent space of the manifold. This way you are given a natural canonical system. And then we also have the vertical distribution. Well, yeah, system, vertical system. V on C is just V alpha, is just the V type. Just the vertical directions. So in picture, let me draw a picture here. So here you have a manifold, say M, and over here we have this projectivized tangent bundle, PTM. And cone structure just means some submanifold here. This is C. And the vertical distribution is just these vertical fibers. These are V. And then we have this canonical Pfaffian system T. That's something here, but let me define one more terminology before drawing the picture. Now, by the very definition, we have an exact sequence from 0, 3, 2. We have a natural exact sequence relating this vertical distribution. This guy is certainly inside this T, and the quotient is exactly the tautological line bundle, because here. So you have this natural exact sequence. Now I define a conic connection. So a conic connection is just is a rank 1 foliation. Inside foliation on C, but this is now contained inside this this system T, such that this intersects with transversal. So in other words, a conic connection is a splitting of this exact sequence. So conic connection is given by this exact sequence. I mean, we are mainly interested in the local geometry of cone structure, but still we have to consider somewhat half semi-global, because along the fiber it's a submanifold, compact submanifold of the projective space, and so the splitting of exact sequence in holomorphic category is a non-trivial condition. So the existence of conic connection is a non-trivial condition. So, but that's the definition of conic connection. And in picture, conic connection just means that you have something in the transversal direction, right? In such a way that its image here give a certain curves, and the tangential lifts of these curves are exactly this this flow. That's conic connection. So this is that. All right. So this so far is very harmless, and there are many situations where you have such cone structure and conic connections. Now the problem is what to study. There are so many examples, and my main interest is originated from algebraic geometry, and in these examples there are very special kind of connection. So let me define this. A conic connection F on a cone structure is, well, C is a characteristic connection if the following hold, if F and the derivative of this T is contained in derivative of this T. Now this just means that it's the derived system. It's T with is the first bracket. I mean, yesterday in Boris notation, this is just 2. So we need this condition that this connection is contained in the Cauchy characteristic of this derived system. So that's an additional condition. So then, so if the connection satisfies this condition, then we say it's characteristic connection. And this is reasonably strong condition because in most cases, this there's a unique. If it exists, it's unique in most cases by this property. So in many examples, often this characteristic connection is exactly the Cauchy characteristic of this. But anyway, so the definition is that we just require that it's inside the Cauchy characteristic. That's the definition of characteristic connection. Now, why do I define all this stuff? So this is a kind of fact, which I cannot quite convince you in this short time. But this, the fact is that there are lots of examples of cone structure with characteristic connections. Arising from algebraic geometry. So in yesterday's lecture by Daiming and also Jaehyun, they discussed these VMRT structures. So they are the origin of these examples. So usually from certain rational curves or lines, by looking at their tangent directions, you eventually get this cone structure. And they are equipped with this characteristic connection coming from the lifts of these rational curves. So as Naiming said yesterday, we studied these algebraic geometric problems using these differential geometry ideas for about 10 years now. But then at some point, I think around last year, I decided that it's just okay to study these structures without any worrying about algebraic geometry. So just this cone structure equipped with this characteristic connection. Because now it seems that whenever you get some non-trivial result about such structure, you can find some application in algebraic geometry. So I think especially for differential geometers, it's a good idea to look at these structures and see what one can say about it. Now, the difficulty is that the definition is kind of quite arbitrary. I mean, one difficulty is that these cones at every point may change from point to point. And then there's no, as far as I know, there's no differential geometric tools to study such structures so far. And I hope very much that people develop tools to study such structures. But at the moment, most of the nice tools in differential geometry. They were developed only in the case where they are sort of transitive, that each cones are isomorphic. So for that reason, today I have to this restriction. So I make this additional assumption. So that's the following definition. So let's our complex manifold say as dimension n, then let V be a vector space. And you pick a submanifold from this projective space. So this is a projective submanifold. Say whole dimension P. I'm not sure whether this will be necessary. So let's pick a submanifold here. And then a cone structure. C is G isotrivial. Now you have this, if for each point, we have this cone, Cx inside. We have the submanifold inside the projective space. Now I require that this is isomorphic to Z inside P as projective submanifold. So that's a very natural assumption. In other words, we assume that each of the cone as projective submanifold are isomorphic to each other over the whole manifold. So this is not just isomorphic as an abstract complex manifold, but we require it as isomorphic as a projective submanifold. And this term, isotrivial, this is what algebraic geometers use in such a situation. That it means it's kind of, as a family, it's trivial, but we don't know what will happen globally. So that's why they put this isotrivial. As isomorphic classes, it's trivial. So that's the term. So now I'll say that whenever this holds, then I'll say it's G isotrivial cone structure. And this is, as I said, it's a rather heavy restriction, because there are many examples in algebraic geometry where this does not hold. But still, to make some computation using differential geometry tools, I make this assumption. And even under this assumption, there are many interesting questions. So, so from now, I will concentrate on this G isotrivial cone structures.
So this implies that it is locally trivial, this cone structure. From this assumption, you get that this submersion is locally a product?
Yeah, locally product as a projective submanifold.
Yes.
Yeah. But not as a, not flat in differential geometry. So I will raise the question soon. So here's the example. This example is probably more familiar to differential geometry. Suppose you have really a Lie group as automorphism of this vector space. And suppose you have a submanifold. So this is a compact submanifold preserved by reaction. Suppose you have such a submanifold. Then a G structure on M induces a G isotrivial cone structure. Right? By just considering the natural orbits. I mean, natural isomorphism. G structure means that you are given an isomorphism where this G action is preserved. So whenever you are given a G structure, there's natural way to put this G inside the projective tangent space. And this way you get a cone structure. And in some sense, for most G structures, I think you can interpret it as a theory of cone structures. So this cone structure, this G isotrivial cone structure is something bigger than G structure in some sense. At least when it's of the first order G structure. So from this point of view, many of the works on G structures can be interpreted as a work on cone structure. And this was one of our main inspirations at the early stage of our work. But I have to say that now the more interesting examples are not of this type, where there's no automorphism. These are more interesting. Well, I cannot say more interesting, but those are what I will be concentrated on today. Not quite of this type. Now one more definition. Which explains the point which Andy just raised. So a G isotrivial construction is flat if there's a neighborhood with a holomorphic chart. The holomorphic chart just means a biholomorphic map from this neighborhood into the vector space. And then such that the differential of phi defines a map from projectivization of the tangent bundle of U to projectivization of the tangent bundle of PU. But this is a tangent space of vector space, so this is canonically isomorphic to PV. And now here we have this cone structure. So if this differential sends this guy to send this to G plus PV, then we say that this is flat structure. This is the usual notion of flat in the sense of geometric structure. You can find coordinates in terms of which this cone structure becomes defined by vector fields with constant coefficients. So our main interest is when cone structure becomes flat. That's the main interest. I mean, when this G isotrivial cone structure. This G isotriviality is, of course, a necessary condition to be flat. I mean, if it's not G isotrivial, then it cannot be flat. So this is a reasonable condition. Now our aim today is the following. Aim is to show that under suitable projective geometry and the isophilia cone structure characteristic connection this is the kind of result we want to have. So we want a condition on this projective submanifold, some projective algebraic geometry condition. That's a condition on this submanifold, as a submanifold of projective space. And under such conditions, we hope to have this flatness of any G isotrivial cone structure, as long as there's characteristic connection. And this means that there's this existence of characteristic connection is a very strong condition, because you can always locally produce, for any G, you can locally produce G isotrivial cone structure, which is not flat. You can just arrange. So the existence of characteristic connection is a kind of strong restriction. And under some restriction on the projective geometry, you automatically get flatness. But as a remark, and if I have time at the end, I will give this example, but there's an example. So not every G isotrivial cone structure with characteristic connection is flat. So for certain G, there are examples with characteristic connection which is not flat. So you do need some additional projective geometry condition to have this kind of result.
But the flatness is not particularly connected with that particular characteristic connection, is it? I mean, the flatness is not for the connection itself. The flatness is for the structure.
But in our example, the flatness comes from this connection. This connection is really
flat.
Yeah. The reason is that, as I said, in most examples, most means that as long as this is non-linear, characteristic connection is unique. If it exists, it's unique. And that's the one source of. Also, in the proof, we need this fact that the flatness really comes from this characteristic connection.
And existence is a strong condition even locally.
Yes.
Yes.
Yes. This statement is a local statement.
And so for G structures, can you say which G structures admit characteristic connection?
That's a very good question, and first of all, let me say that for our result, these structures do not apply.
Okay.
And second, I think there are G structures coming from Hermitian symmetric space, which Namin talked about yesterday. For those allow characteristic connection. For those, the cone is the highest weight cone.
Yes.
And they have a characteristic connection coming from the rational curves. And in that setting, Naiming earlier proved a version of this, but somewhat global version. It's not completely local version. So even in that case, the completely local version is not known. So let me state the main theorem, then you can see what kind of result talking about. Okay, here's the main theorem. So Z is a projective submanifold satisfying. There are the following four conditions. This is, let me write this way. So this is the, this means the holomorphic sections. And this is this O1 bundle. And I assume that the holomorphic sections of this bundle on this manifold has dimension exactly n. So that's the condition. And this is in algebraic geometry. This is usually said mentioned as G is linearly low mass. 2, I assume that this gamma is 0. And here this means the traceless endomorphism. Of the tangent boundary. See? The set of tangent lines is Z. The set of tangent lines can be regarded as a subset in this second exterior power of the vector space. And this set of tangent lines G generate. So they are non-degenerate inside this space. That's another condition. And 4, gamma G. This is 0. So I consider projective submanifold satisfying these 4 conditions. It's rather complicated. So if you don't understand, just regard them some complicated conditions. But this is purely in terms of the projective geometry. Then any G isotropy construction with surface connection is flat. So this is the main result, which shows an example of this kind of philosophy. That you can give some projective geometry condition under which any isotrivial construction with character connection is flat. Now let me remark that these conditions hold for hypersurface, smooth hypersurface. So these give examples. To check that they satisfy this condition is also non-trivial projective. It's algebraic geometry part, non-trivial. But anyway, there are non-trivial examples satisfying these 4 conditions. So in other words, whenever you are given a cone structure by hypersurface, smooth hypersurface, such that the degree here means that this is defined by homogeneous polynomial equation, and this homogeneous polynomial has degree at least 4. So whenever you have a cone structure given by hypersurface of degree at least 4, and if it is isotrivial, and if it has a characteristic connection, then it must be flat. So that's the case, one example of our main theory. So let me now try to, in the remaining 15 minutes, try to give you an idea of proof of this theory, how something like that can be proved. Now, you see that, as you see over the example of hypersurface, our cone is quite far from homogeneous variety. There's no G structure. And smooth hypersurface of degree at least 4, that they don't have any continuous automorphism. So these are very far from this example coming from G structures. There's almost no Lie theory here. So what has to be done is, I look at all differential geometry literatures. But when you have no Lie group, there's very little differential geometry theory. So I had to go back all the way to the original paper of Katan, where he studied very general equivalence problem. And that's our tools. So we go back to the Kaltan's original formulation of equivalence problem. Okay, so the Kaltan method. So here, of course, the main thing is that this G isotriviality without any automorphism, it naturally gives rise to absolute parallelism up to projective equivalence. So we look at this co-frame. So let me remind you, although most of you are more expert on this than I, but let me remind you, it's co-frame, so this means absolute parallelism. On M is a V-valued one form, omega, such that omega x, now it's one form, so it gives a map from tangent space to the vector space. This is an isomorphism. So such a vector value one form is called a co-frame. And I say that a co-frame is conformally closed if E, F was a function, holomorphic function. Okay. So this is, I'm just declosed with this. So I assume, I say that it's conformally closed if up to reparametrization it becomes closed. Yeah, up to rescaling. Now, given a co-frame, there's a unique function on M with the values in this homomorphism are, say, unique function sigma. Well, let's write it sigma omega. So called the structure function omega, such that V omega is sigma. So both sides are V-valued. This is V-valued 2 form, and this is well-scale V-valued 2 form. So there's a map. There's homomorphism sending this guy to this guy. So that's the structure function. So this is the generalization of structure function in the over D group. Now here's a small proposition. So this describes structure function for conformally closed. So let I denote it by CD. Is by that this is a subspace in this. Defined as following. So this is just this is a homomorphism satisfying this property. That when you are given two vectors u and v, its image is in the span of u and v. That's the. Okay. So let's consider this subspace. Then omega is conformally closed. If and only if its structure function has values in this space. Here I assume that the dimension is at least 3. So under this assumption, the conformal closedness is equivalent to the fact that the structure function has values in this guy. Now, I guess this must be known, or I don't know, but I cannot find the literature. But this is certainly Cartan must know how to prove this. So also, most of you know, if you know the answer, then you can prove it. And you can give it as an exercise to students. So you can see now that what we have to do to prove the main theorem, that we need to find a co-frame with this property. And how? So, but we have to relate it to the cone structure. So here's the additional. Given G isotrivial. A co-frame is adapted. See here. So adapted co-frame means that the isomorphism induced by this co-frame sends our cone to this Z. That's a very natural definition of what of those co-frames which are compatible to our cone structure. So whenever you have such a, so you have to work with such a co-frame. And it's, you can always find lots of such co-frames because by the definition of isotriviality means that you can find co-frame adapted to this. Okay, then the next observation is almost immediate. So this is proposition. This is flatness. How to prove flatness of construction? C is flat. We can know it. There it is. Adaptive co-frame. Which is and this is just a statement of Poincaré lemma. That if you have a conformally closed co-frame, then by this rescaling, you can make it as a closed co-frame, but it's still adapted because the adaptation is for the projectivization. So if you multiply the co-frame by some function, it's still adapted co-frame. And if it's declosed, it means that it's flat by Poincaré lemma. So this is just a Poincaré lemma. So that's what we need. We need to find a co-frame, adapted co-frame, which is conformally closed. And by this proposition, what we have to show is that there's an adapted co-frame for which the structure function takes values in this space. Now the next proposition. So I cannot give a proof of all these, but I think the proposition explains kind of the idea how the proof can be done. So the individual propositions are not too difficult structure function of characteristic connection. So now I have to relate it to characteristic connection. So this is cone structure with G isotropic. And omega is adapted plane. Now here's the condition. The adapted coframe induces a conic connection. On C. This is by geodesic flow. When you are given an absolute parallelism, you have the notion of geodesic induced by this. So, and this geodesic flow preserves this C because it's adapted. So whenever you have adapted coframe, you have induced conic connection. Now, if this induced conic connection is a characteristic connection, then its structure function takes values in the following subspace. So this is now Z, and this is inside the home. It's the following set. So it's a homomorphism from the square root V, and required sigma U V is where this G hat is cone over G, and U is a point in G hat, and V is a point in the tangent space. So there's a distinguished subspace of these homomorphisms determined by this submanifold PV with this property that I'm looking at those homomorphisms which is sort of send the tangent planes to the cone to itself, to inside the tangent plane and to the tangent space. So this is a distinguished class of homomorphisms determined by the projective manifold. And the statement of this proposition is that if this coframe induces a characteristic connection, then the structure function must take values in here. And I cannot give you details of the proof, but roughly speaking, this condition here, this is a reinterpretation of this condition. This condition for characteristic connection. So you can see, you can interpret, I mean, you can imagine how such a condition arises. There's the same guy twice. This is essentially the same guy twice. And the U is the kind of the direction of the characteristic connection. So this is an interpretation of this condition in terms of projective geometry.
What did you write on the last line? Second last line.
Cone over. So when you are given, when you are given a submanifold, then you have this cone inside the vector space. That's the union of all the lines determined by G. Okay, so up to now it's there's no projective geometry coming. And here's the essential projective geometry part. So suppose G is a submanifold. Satisfying. Well, I erased it, but I wrote 4 conditions. Suppose you satisfy the first 3 conditions, then this is the same as this subspace of the homoprisms satisfying this tangential condition is exactly the same as the one. This one I also erased it. But this is for conformally flat, conformally closed frame, co-frames, the structure function, and this is now coming from this. So the condition we need for conformally closed co-frames agrees with the condition coming from this characteristic connection. If this G satisfies the first 3 conditions. So this is the part we need, this projective geometry condition. That we identify these 2 restrictions on structure functions by this. But still it's not completely done, because as Mike mentioned at the beginning, it's not clear whether given adapted coframe has the characteristic connection, and even if it has a characteristic connection, whether it's exactly what's induced by adapted coframe. This is not clear. So suppose you have a cone structure with characteristic connection. Now we need to show that you can choose a coframe whose induced conic connection is exactly this characteristic connection. This is non-trivial. And this is, in a sense, most difficult part, I think. And I sort of try to avoid this difficulty. By the following easy way, so proposing the uniqueness of the change. So this means that if Z satisfies 4, the condition 4, then G I to G has unique conic connection. And this is because this condition 4 was the vanishing of this. Vanishing of this was the condition 4. But the space of the set of conic connections is isomorphic to gamma C T C. The set of conic connections is actually isomorphic to this holomorphic sections of this bundle on C, because this means it's just a set of splittings. So set of splitting of such exact sequence is exactly this guy. So
you mean if it has a splitting? If it has a splitting?
Yeah, if it has a splitting,
so
then
it has a connection that is unique.
Yes.
Yep.
So for any G isotrivial cone structure, if it has conic connection, it's unique, as long as it satisfies the condition 4. So now from this we can now prove it. Oh, so I have to go back. So the proof is proof of many theory. This condition 4 gives the uniqueness. So any adapted co-frame induces characteristic connection. Because there's unique conic connection, and we assume that there's a characteristic connection. And then by this projective geometry, this G equals sigma B. So co-frame omega. So the sigma omega has value. And that means it's flat. So that's how one proves. Okay, I have to stop. Thank you.